Yeah, that's pretty good. Okay. $9.15 now. Is there anything we want to put on the board, do you think? I don't know. I guess we're recording. Holy cow. And I'm 15 minutes early. I don't know if I need to be that early. I don't have any customers yet. Oh, well. Probably should do one of these more circle things. Okay. Why don't we do number 4? That'd be good. All right. Yeah, we'll do number 4. That'd be good for us. Yeah. Okay. So I need to draw this 50. Yeah. Okay. We could probably do that. Okay. And we'll come over here 50. There we go. Hey, we've got Kristen online. Hello, hello.
How are you today?
Oh, not too bad. Have you had your breakfast?
No, but I'm working on it. I've got a bagel in the toaster.
Oh, good deal.
Yeah. I do have my coffee though. So, that's what's really important.
I thought maybe we'd go over any of those more circles that are bugging anybody.
Yes, I was struggling with those.
Okay, well, we certainly do that. See what I've done here? This is number 4.
Yes.
And I went over here 50. And I went up 30. If this goes down, you got to go up. And
Okay.
then here is 10. So I got to come over here 10. That puts me right there. And then see, if I went up before, I got to go down now. So I got to go down 3. That puts me right here. All right. So there we go. Now,
Yeah, I don't think that's what mine looks like.
uh-oh, Spaghetti-O.
Okay, so you went over 50 first,
Yeah,
right?
look here. I went over 5 inches for 50,
Okay.
and that goes down 30, so I go up 30. See the 30?
Yeah.
Yep, that's 30. And then that's 10, so I go over 10, that's 1 inch. And since I went up before, I got to go down now, I go down 30.
Well,
So,
why do you go left 10?
well, if it had been compression, I would have to go over here because see, compression's negative and tension
Okay.
is positive.
So then you went 10 to the left of 50. So that's at 40, right?
Well, it's 50 from here,
Right there.
from here
Yeah.
to here.
Oh,
Look here, 5 inches,
right. Okay.
50.
Okay.
Now this is 10 here, 1 inch. You go to the right,
Oh, so you just started back at the x-axis and then went over 10
right. Now,
at the origin. Yeah.
this is your anchor point, I call it. Now, if you'll draw a line between there, you'll have a diameter of your Mohr circle. There it is. Now we need to know these distances here. Well, see if that's 50 and that's 10, that's 40. You know what this here is 20 and that's 20. Did you follow that?
Yeah.
Okay, you got a 20 and 30. Now I'm going to get my calculator and find out what 20 squared plus 30 squared, 20 squared plus 30 squared, square root. It's 3605. This is 36, rounded off to 6. And I can tell you what this is right here. This is at 30. And when you draw your Mohr circle, 3605, let me draw my Mohr circle. Let's see, 3605 will put you about out here. 3605. I'm going to draw my Mohr circle. 3605. 3605. 3605. Yeah, here goes. Here, 3605. Here goes Mohr circle. Dun, da, da. Dun, da, da. Dun, da, da. Now, isn't that a pretty thing?
That is. Now, I'm trying to find my, yeah, I did that all wrong.
Yeah, I've been grading some of the different people,
It's all wrong.
and in fact, I probably graded you. Let me see what I gave you.
I'm sure it too. It was bad.
Maybe. Yeah, we're not going to mention what it was because.
Yeah, it was bad.
Yeah, but that's okay, Kristen.
We still get at least 2 points though, right?
Absolutely, and I want you to know how to do it for the final. See, the final's coming up, and there'll be one on the final.
Oh, I know. That's why that's why whenever I saw you were doing this, I was like, oh yes, I need this because
Yeah.
I was having issues. Okay. So
Now here's the most important thing of all. That's your maximum normal stress. It's tensile. And see, if that's 30 right there, and this radius is 36, that makes it equal to 66.06 megapascal.
Now, I did somehow come up with that number.
Bless you.
So that should be worth something. I actually got
Absolutely.
66.06 megapascals.
Absolutely, it should be worth something. Now, now you can even get the angle. Now, all angles are measured from this anchor point right here. And this angle right here, going clockwise, is negative. See, counterclockwise is positive. And
Right.
if you want that angle, what you do is you take 30, divide by 20, hit the arc tangent. It's 56.3. This angle here is a double angle. It's 2 theta. It's 56.3 degrees. So this angle here occurs, the theta is half of 2 theta. So you divide by 2, it's at 28 point, running out of room over here, 28.15 degrees. Now what we could do to check that, if you don't believe it's right, is we could go to our, what they call those stress transformation equations, and we could plug it in. See here's the stress transformation equation. And this, hey, we got another customer, Caitlin. Welcome, Caitlin. Caitlin, we're doing number 4 here. Just class hasn't started yet. We have 4 more minutes. We're checking this to see if this is right. And here is the formula. Well, you guys all have that formula. Maybe I should write it. Oh, by the way, this formula is on page 451 in your book. Okay, now we're going to plug that in and see what happens. Okay, well, if you add these two, if you add 50 and 10, I get 60. And so 60 divided by 2 is 30. So what we have is 30 plus, well, no, that's 50 minus 10. That's 40 divided by 2. That's 20. And the 2 theta, we decided, is 56.3. And this little guy here, what's confusing is, I think, because it's going down, that's going to be a minus 30 sine of 56.3. A little bit confusing. Now wait a minute. Auga. This is going clockwise, so it's negative. This angle is a negative 28. So this is a negative 50. I'm sorry this is so dang complicated. That's a negative 56.3. Now, if we plug all this in, let's see what we get. Question mark. I wonder what it'll be. Well, don't know. I'm going to plug it in here and we'll see what happens. Let's see, 30 plus 20 times 56.3 negative cosine minus 30 times the sine of 56.3 negative sine. And here's what I get, guys. When I plug all that in, I get 66.05. Oops, ran out of room. Megapascals. Well, Shazam, that's what we got using the Morse circle, isn't it? So this stuff works pretty good. There's number 4. That's what number 4 should look like. On your homework, some of you guys only did 1 or 2 Morse circle. I intended for you to do all 6. Maybe that was asking too much. But there's number 4. Go
I
ahead.
misunderstood that then. I thought we were just supposed to do number 4.
Oh, that's my fault. I think maybe I owe you a point if I miscommunicated there to you.
Well, like, that's what I thought. I'm not saying that, like, hey, that could be like completely on me. I mean, maybe other people understood we were supposed to do them all. I'm just saying that's the reason why I only did number 4 is because that was my understanding.
No, you're not the only one. There's several that did that, but then there's some of you guys that did all of them. Some of them did 3 or 4 of them. So main thing, I just want you to be able to do it good on your final. Well, there's number 4, and we could do another one if you wanted. I have other stuff to do today, but I'm still waiting for some more customers. Let's go down here and see who's here. Oh, look at here. We have a whole slew of wonderful students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have, right now, we have 12. Maybe there's more. Maybe it runs off the page. Let's see. Go over here and run off the page a little bit. Oh, no. I pushed the wrong. Oh, gee, I pushed the button and something bad happened. Oh, I don't know if I'll ever be able to get back. Let's see if I can. I don't know.
You'll figure it out, Professor. I believe in you.
Yeah, there. Now I'm back. I won't do that again. But we have. Hey, was that Gavin?
Yes, Professor.
Yeah, Gavin Shepard.
Yes.
Gavin, I had a student by the name of Jeremiah Shepard a few years ago. Is that any relation?
No, Professor. I'm the oldest of my family.
Just thought I'd ask. I had that student, and I wonder if they're related. Okay, well, I'll be glad to do another one of these if you want. Now, I never did do the. Why don't we do that? Well, that's going to be your maximum shear stress. And it's just equal to the 3606 megapascal. And you can even get the angle it's at. Now the angle it's at, be careful, all angles are measured from this anchor point. So you'd have to go all the way down to here. And that angle is, I believe it's 146.3. You'd have to add 90 to 56. Well, that's the double angle. 2 times theta is 146.3. So half of that would be 146.3 divided by 2. And it's negative because I went clockwise. So it's negative 73.15 is the orientation inside your piece. Did anybody have a comment or question on any little old thing for me right now? Well, okay. There's a little bit of review there on your Morse circle. That's good. What's next? Well, I want to go through kind of a review thing here. This is going to go back a ways. to stuff we've studied. If I can find what I want here, hang on a minute. Yeah, here we go. Totally organized.
Hey, Professor.
Yeah, I'm listening.
So with the Moore's circle, does that demonstrate all the types of stresses that are impacting the body at the same time?
Yeah, it gives
So,
it gives you the tensile stress, it gives you the compressive stress, and it gives you the shear stress.
okay, so all of those forces are acting on the body simultaneously?
Yes.
Okay. So so that is kind of like the be all and be of what we're talking about with tensile stress and stuff like that. This is like,
Yeah. Remember, stress is the name of the game.
okay. All right,
Stress
thank you, Professor.
anytime. Stress causes problems. Okay. Well, we're going to go through a problem in detail here. This is fundamental problems. I love the fundamental problems. Uh, and it's fundamental problem 8.3. We are going to do fundamental problem 8.3. And I thought we could just work on it to where we really understand it. That's the plan. Okay, now first we got to draw our free body diagram. And so let me do that. I think I do better standing up sometimes. You know, I could even do this to scale like you guys are supposed to do. If you go to your book, I don't know what page it is, but it's,
Page 430.
hey, thanks so much. And what we need is, trying to figure out a good scale here. I'm thinking maybe this would be a good scale. Okay, now this is, the way I understand it, it's 0.5 meters. Yeah, it's 0.5 meters. And this is 0.5 meters. And this is 2 meters. Now I've done those to scale. This is 2 meters and that's 1 meter, and they're done to scale. And this has a smooth pin here. And this has a roller. And we have a 30 kilonewton force right here. Now my wife got me some red pencils. Let's see if these red pencils work. I don't know. We'll try it. See, I like my forces in red, but does this come out? Does it come out in red? Let me look and see here. How come on my screen this is a red pencil? Yeah, it says red. It's bright red, but when I write it, it's just sort of black. Never mind the red pencil.
I mean, it's distinct enough.
Yeah, it's kind of red. Okay, and they said that that's 30 kilonewtons. That's supposed to be straight down. There we go. 30 kilonewtons. Now the first thing we're going to do is we're going to find out what A and B are. Now we're going to call this A. and we're going to call this B. And I'm going to shut up for 2 minutes or a minute and a half or whatever. And I want you to find A and B. Go for it. Find the force at A and the force at B.
Is the total distance between A and the force 1 meter? It's difficult to read that.
Oh, you can't read it? It's 0.5 meters and 0.5 meters.
Okay, thank you.
Yeah, so there's 1 meter to there. What do you need, bud?
I need help on math.
Show me.
On an improper fraction.
Okay, well now you could count those.
Well, on this one.
Oh, on this
it says
one.
to put a mixed number fraction and an improper fraction.
Well, see, there's 1, 2, 3, 4, 5, 6. There's 8 of those, but there's 9 total. So what's 8? Mixed number and a proper fraction of each. Guys, I'm doing a 4th grade problem here for my grandson, and it's a little bit over my head here. Write a mixed number and improper fraction for each shaded model.
Oh, it's Common Core. I can't do that.
It looks like you have.
I have my mixed number fraction.
Oh, I see what you're saying. There's 1, there's 2, and 2/3. Yeah, I like it.
But then I need an improper fraction.
Oh, well, 2 times 3 is 6, plus 2 is 8, so it's 8/3. That's what I said in the first place, wasn't it? Or maybe. Look, can you see there's there's 8. 2 times 3 is 6, plus 2 is 8, so you got 8/3.
Okay, thank you.
Okay, anytime. I don't know. It's pretty complicated. Okay, you've had a minute. Here's I'll give you another half a minute, and then we need A and B. And this problem is in your book. It's F83, Fundamental Problem 83, page 430. Let me see if it really is on page 430. I'm going to look it up. Yeah, there it is. Good, excellent. That's it. Okay, well, I got my answers. I came out with 10 kilonewtons here and 20 kilonewtons here. Now, I'll be glad to go over that for anybody that is in doubt. Just speak up. Unmute and speak up. Otherwise, I just assume you're okay. Nobody said anything, so I guess you're okay. Now here's what we're going to do next. We're going to write the shear and bending moment loading diagrams. So here, let me do that. Here we go. We're going to do the shear loading diagram. Here goes. Da, da, da. It's going to be kind of messy. Sorry about that, but we'll be okay. And then we're going to do the bending moment loading diagram here. Here we go. Come on now. There we go. Okay. Now I'm going to give you another minute to write the shear loading. We're going to write the shear loading diagram. Let me scoot that 20 kilonewtons over a little bit. See, this is going to be the shear loading diagram. And this is going to be the bending moment loading diagram. Go ahead, I'll give you another minute, and then we'll do those. Do you remember how to do that? What you do is you take a left-hand section. Take a left-hand section. Shear going down on a left-hand section is positive. Well, did you get a shear loading diagram that looks like this? Where this is 20 kilonewtons and this is minus 10 kilonewtons. That's the shear loading diagram. Does
Yes,
anybody,
Professor.
are you happy with that? If anybody wants me to, I'll go back over why that is. Okay. And now the bending moment loading diagram.
Because I think I arrived late.
Say that again, please.
Yeah, please go through that. Sorry,
sure.
I arrived a bit late.
Yeah, sure. Yeah. I'm trying, that voice is so familiar. Was that Heath? That wasn't Heath, was it? Yeah, it was Heath.
Yes, it was.
See, I'm getting to where I know your voices. See, how about that? Okay, now Heath, what you do is you cover this thing up and you just look at that section. You see that force going up there at A? Well, there's got to be a force going down on that left-hand section of 20 kilonewtons. Shear going down on a left-hand member is positive. So that's how come it's a positive. Now, if you cover it up here, any place in here and look at the left-hand section, you got 20 going up, 30 going down. You have to have 10 going up for equilibrium. Some of the forces have to be 0 on the left-hand section. Well, 10 going up is a shear force that's negative, so it's negative 10. Heath, did that make a lick of sense?
Not too much, but I think it's because I can't really see it on my screen.
Okay. Well, maybe it'd help if I drew the section. I got some room over here, Heath. What I'm going to do is, actually, they want us to section it right here. They're going to call this section AA. And I'm going to section this thing at AA. Here's our section. And here's this roller. And here's this force of A of 20 kilonewtons. 20 kilonewtons going up. Now Heath, see that 20 kilonewtons going up? There's got to be a 20 kilonewtons going down because the sum of the forces on anything in our class is 0. Now it's a definition. That's a shear force. See, shear is always perpendicular to your axis. It's going down. See, the normal force would be along your axis, you know, where you're stretching or compressing. But this is a shear force.
Okay. I think I'm with you.
Yeah, we've done that before. All right, now we're going to do our bending moment. And there's an equation for that. It goes like this. The difference in your bending moment Oh, by the way, you can tell that it's going to start at 0 because that roller can't give you any kind of moment. And this smooth pin here at B, the bending moment will be 0. So it starts at 0 and ends at 0. And we know from calculus that that's the area under your shear graph. Well, here's your shear graph. What's the area of 1 meter by 20? It's 20 kilonewton meters. So see, this goes from 0 up to 20 kilonewton meters right here. There you have it. And that's 20 kilonewton meters. And then there's a gradual slope. There we go. A little bit crooked, but we tried. That another way of looking at this is that the shear is equal to the slope of the bending moment. And see, this slope is negative. It's supposed to be a straight line. Maybe I can do better than that. There we go. That's a little better. And see, this slope is negative. So that's how come it's negative 10. And this slope is positive because that's how come that's a positive 20. These are some of our equations that we can use. So we just figured out our bending moment and our slope. But see what they want us to do. They want us to locate this thing at this section right here. They call this section AA. And here's what we get from all of this. We found that the shear force on this section AA is 20 kilonewtons. And we found that the bending moment at section AA is, well, it'd be 10. Can you guys see that it's 10 kilonewton meters? Because see, that's 20 there, and that's halfway, so it's 10. We went to all that trouble to get these two numbers. Any comments or questions? We're kind of having a little sort of a review session here of some basics. That was pretty basic there where we solved for the 10 and the 20. Because you take a moment. What I did was I took a moment about A, and I got negative 1 meter times 30 kilonewtons, and then I had a positive B times 3 meters equals 0. Uh-oh, ran out of room. And when you solve that, you get B is 10. That's how I got it. And the 10 and 20 add up to the 30 going down. So if you're y'all, little Southern talk, if y'all are happy there, we're going to move on. Okay, I'm going to erase all that stuff. We went to all that trouble. I've lost my eraser. There it is. We went to all that trouble to get these two values here. Now, what do we need those values for? Well, I'm going to have to erase all this because I need the room, guys. See, I only have a limited amount of room here. But you ask if you have a question about anything. Okay.
Dr. Griffin,
Yeah, go ahead.
I don't necessarily have a question, but can you upload last week's lectures onto YouTube?
Yeah.
I had a missed class all last week.
We did that last night, Heath, and those are on YouTube.
Okay, thank you.
Yeah. If they're not, well, let me know. But,
when I looked yesterday, Thursdays were not on there. The last one that was from April the 9th.
Yeah, we did it last night.
Oh, okay. Yeah, then I didn't look since then.
Yeah,
But
do it today, and all my lectures. Well, this one isn't on because I'm not done with this lecture yet. But all my lectures were, well, except one. I think there's a physics lecture that goofed up on. But we're getting into the groove now. We're getting where we're putting them online, okay, or on YouTube, I should say. Those of you that just tuned in, you wonder what we're doing. We're kind of going over some basics. We're doing fundamental problem 8.3, and I tell you what we've got so far. We have these. Now, what good are those? Well, they show up in these equations here. Now, we've studied those equations. This is called the flexure formula, and this is called the shear formula. They're both dealing with bending. We have a beam, and it's being bent. It's sagging. I drew it a while ago, but you can find it on page 430 if you want to see what this beam looks like. I had to erase it because I'm going to need the space here. But notice both of these equations have this I in it, so we have to solve for I. And again, this is just a review kind of basics, but sometimes it's good to go over basics. All right, well, let's see if I can draw this to scale, okay? All right, here we go. I'm gonna draw this cross section of this beam. I'm gonna do it like you guys do it. You do it to scale, I know you do. Okay, so we need 18. All right, here we go, 18. Yeah, it's a foolproof plan here. And there's 18, and then we have 100. Well, that would be 10. Okay. Now how wide is this thing? It's 10 wide. So here, let me make. Come on now. There we go. I'm doing this to scale. It's a foolproof plan, and now I need 10. Okay, we can do that. Here we go. And we need 10 down here. Okay. Ta-da! All right, I did that to scale. Where did I get that from? Well, I got it from page 430. We're doing fundamental problem 8.3. And you have to find this I thing, this moment of inertia thing, in order to solve for the stresses. Okay, well, now this distance here is 180 millimeters. This is 10 millimeters. These are 10 millimeters. 10 millimeters. 100 millimeters. 100 millimeters. Well, I've tried to draw it to scale. Okay. Now, we know where the centroid is for the whole thing. For the whole, this I-beam, the centroid would be there. And they've got a position there. They want us to find the stresses. Well, let me find where that is. They said if you come down 50 from the top, That puts you right here. 50 from the top. This distance right here, they said is 50 from the top. If you don't believe me, go to page 430 and see it. That's what they said. So, so what? Well, what does that make this distance here? Let me think about that. Don't know. It'd be 90. You know what? I think that distance is 40 millimeters. Here, I'm going to measure it and see. No, that comes out more like 50. They said this was 50. You know? Okay, now I'm having a little trouble there. I guess that's wrong. They said it's 50 from the top.
It makes sense if you add the 180 and the plus 10, then it's 200. And then 50 plus 50 is 100, so that's like half of 200.
Oh, okay. So it's 200 for the whole dang thing, right? Yeah. 180 plus 10 makes 200. For the whole thing, yeah. So it's 100 from here to the top, isn't it? Yeah, so it is 50, isn't it? From the center of the whole thing to here is 50. From here to the top is 50. What do you think? Yeah, by Jove, I think that's it. Well, look, it measures too. I'm measuring with my ruler, and that's 50. And by Jove, that's 50. Okay, so what? Well, we got to figure the moment of inertia of this thing. All right, well, let's do it. Here goes. Now, one way to do it, I know I've shown you this before, is to subtract these negative areas. So let me do that. One way to do it is to go 1/12 times the 0.1 times the, you said it's 200, right? 0.2 cubed minus 1/12 times these areas that I'm going to subtract. Well, there's two of them, and they're, how wide are they? I don't know. The total would be 90. I'm just going to go 0.09 times 0.18 cubed. That should give me the moment of inertia. You'll understand what I'm doing. I'm subtracting the areas that aren't there. Gee. Well, here goes. I'm going to do that. Let's see what we get. We'll know in a minute because I'm going to do it another way. Okay, there's 1/12 times 0.1 times 0.2 cubed minus 1/12 times 0.09 times 0.18 cubed. Okay, here's what I'm getting. I'm getting 2. I'll write bigger. Maybe you can see me. The 2.293. There's a bunch of 6s. 10 to the minus 5 meters to the 4th. Nope, meters to the, yeah, meters to the 4th. That's right. Yeah, now let's do it a different way and see if we get the same answer. Doing it a different way, we'll take this bottom piece, which will be 1/12 the 0.1 times 0.01 cubed. You have to use the parallel axis theorem. We need the distance from the center of the whole thing to the center of the flange down there. Well, that distance there from the center of the whole thing to the center of the flange is 95. Guys, it's 95, isn't it? Yeah, it's not. So it's 0.1 times 0.01. That gives you the area times 0.095, I believe, squared. Now, there's 2 of those babies, so you're going to have to multiply that by 2. Plus, we got to do the web. And the web is 1/12, 0.01, 0.18 cubed. Now, if you do all of this, you should get the same number. Here goes. I'm going to see if I get the same number. All right. I'm plugging all this stuff in now. Okay, now here's what I'm getting. I'm getting 2.29, 26 times 10 to the minus 5. Gee, it's awfully close. Something bad happened, guys. I'm going to have to do this again here. 29. I think this answer is right. 2 and 2, 9, 2. Let me do this one again. I think I did this one right. But let me stare at this one a minute. Times 0.2 cubed, yeah. Yeah. Minus 1/12 times 0.09 times 0.18 cubed. I wonder if I ever did that. Let me check this calculation again. I want it to be right. I don't want to give you any bad stuff here. I'm getting 2.29. Yeah, that's a 2.6. I pushed the wrong button or read it wrong. But no, it comes out the same. I did that to make sure I got that right. I did it 2 different ways. Do you have any question on those 2 different ways of finding that moment of inertia? It's important. We got to have it in both of these equations. Any comments or questions on that? Well, nobody said anything. So we do have our moment of inertia now. We'll circle it. We know what it is. It's this 2.2926 times 10 to the minus 5th meters to the 4th. So we got that. Well, so what? Well, what do they want us to do? Read it. It says they want stress. That's what this class is all about. They want the stress at this point right here. They want both of these. See them? Well, look at here. We know what the bending moment is. Look, we figured it out a while ago. If you tuned in late, we did it. You could rewatch the video. And see how I got that? And we did this too. Look here. We did that too. Now the thickness is no problem. The thickness here is just 10 millimeters. So we know what that is. We haven't figured out this Q thing yet. Now, what's this Y thing? Well, Y, remember, is the distance from the centroid to wherever it is that you want to find your normal stress. Well, the Y in this case would be, there it is, there's Y. It would be your 50 millimeters, wouldn't it? So we know what the Y is. We know all that stuff except for the Q. If we can get that Q, we can get the stresses. Okay, let's do this one. We know all that stuff. So here we go. There's some room right here. See this room? We can get that. Now the minus, refresh your memory. The minus, this Y is going to be plus. That's plus, that's plus. You're going to get a negative answer, which is compression. Remember, on these beams, it's compression on the top, tension on the bottom. Remember that? When you have a beam and it sags, you put a load on it, it sags, you got compression on the top, tension on the bottom. Okay, well, here goes. We're going to plug this in. We got a minus a 10 kilonewton meters times Y. Well, Y is 50, so that's 0.05 meters. And we're going to divide by I. Well, I is down here. We did it two different ways. So I'm going to do that now. And we are going to find the normal stress. It'll be compressive, acting at that point. That's what they wanted us to do, and that's what we're doing. Here goes. Okay, let's see. 10 e to the third times 0.05 divided by 2.2926 e to the minus 5. Well, I got an answer, and my answer says 21.8 megapascal. That's the compressive stress. Now you can put a minus sign on there if you want to remind yourself that it's compressive, but we know it's compressive. So I wonder if that's what I got. Let me look and see here. See if I got that. We're having a review here, kind of going over some basic. Yeah. Wait a minute. Got lost here. Yeah, 21.8. Yeah, that's it. By Jove, that's it. That's the normal stress. Now we're going to get the shear stress at that location. Did they ever give it a name? They call this location A. And we just found the normal stress at location A. It's 21 something megapascals compression, compressive stress. Now we're going to do the shear stress. We know V is 20. We did that. We know I. We did it two different ways. Let me caution you about this business of subtraction. That only works if your cross section is symmetrical about your y-axis. See, this is symmetrical about the y-axis. But like if you had a T, for instance, I've had students that try to use this subtraction method on a T. You can, but it's much more complicated. What they did was they took these areas here and they subtracted them, and they got the wrong answer. Don't do don't do this subtraction method with something that's not symmetrical. Y-axis? No, it's the x-axis. Sorry. See, this is symmetrical about the y-axis, but about the x-axis, it is not. It has to be, put it this way, it's got to be symmetrical about both axes. Axes, plural of axis. Well, if you just tuned in, welcome to our Strength and Materials class. Today is Tuesday, April 21st. We are doing fundamental problem 8.3, kind of a review to try to bring you up to snuff, because you're going to have a final exam. Most likely, I won't ask you to do everything we're doing here on a problem. This is too much. But I could ask you for parts of it, like I could ask you to find the moment of inertia of a cross section. Or if you knew some of these things, I could ask you to find these things here, just little bits at a time. Okay, now all we got to do to find this shear stress is to find this Q. That name of that is first moment of area. And we're going to do that now. Okay, here we go. We are going to find Q. And I'm going to shut up. I think I'm going to make some room here. I could get rid of one of these. You don't need both of them right now. Yeah, see, that gives me some room there to do that Q here in a minute. But I want you to see if you can get it. I want you to find Q at this location right here. I showed you how to do it. I'm going to shut up for a minute and a half. Find, what we're doing right now is we're trying to find Q at this location A. Go. And I'll help my grandson. Yeah, go ahead, bud.
I would ask Nana during class, but I don't want to get chewed out waking her up.
Oh, no, don't wake her up. Oh, that could be bad.
So on this one it says,
This one?
yeah, write the amount of hours you spent on the trail as a mixed number. 2 hours and 15 minutes. But
Okay.
how would I write that?
Well, there's 60 minutes in an hour, right?
Mhm.
So it's 2
Oh, wait. 2 and then
15/60th, right? Isn't there 60 minutes in an hour?
2 15/60?
Yeah.
Yeah. Thanks, Papa.
Only you want to simplify the 15/60th.
What do you mean?
Well, you see, 15/60th is equal to 1/4, isn't it?
Well,
I think it is. So you got 2 1/4 hours is what it meant. That's what they want.
so 2 3/4?
No, wait a minute now. Say it again. 15 minutes.
Okay.
15 minutes is not 3/4 of an hour.
Joe Quinn reached the end of the trail in 2 hours and 15 minutes.
Yeah.
Write the amount of hours he spent on the trail as a mixed number and as an improper number.
An improper number would be, here, let me write it down here.
Fourth grade math, Papa.
Yeah. My students, I bet, could do it. See, what we have is 2 1/4. Actually, what we came up with was 2 15/60th.
Mhm.
But I told you that's a quarter.
Yeah. So you could.
Now, an improper number would be 9/4.
So those are my two answers.
This would be the improper number. This would be the, what do they call it?
Mixed number.
Yeah.
So 2, 4, and then 9/4. All right, thanks, Papa.
Anytime.
Just don't want to get chewed out by Nana. You know how
No,
she
we
does like to
we
eat.
don't want to get in trouble. Okay, guys, I gave you time to work on that cue. Here goes. I'm going to do it now. And look, I got some room here. Q. Gee, nobody's ever said anything in a long time. I got to make sure that you guys are still alive. Eric, unmute and say hi, please.
Hi.
Good. Eric is with us. Good deal. So you guys are there. All right, now here goes this Q thing. Now the way I taught you guys is you draw a line through the place that you want to find this first moment of it. Draw a line, and then you color the stuff above the line. Now there's actually two places, so we'll do them one at a time. I'm going to color that there. And see what this is it's the sum of the y bars times a. That's what it amounts to. It's in this case, this distance here, I think, is 40. Well, no, it's 20. See, from here to here, it's 40. From here to here, it's 40. So from here, but wait, that's 20. But see, you measure this from the centroid of the whole thing. So if that's 50 and that's 20, this would be 70. It'd be 0.07 times this area, which is 0.01 times 0.04. But we're not done yet. We got to do this area here. Okay, here we're gonna do this area here now. I'm gonna color it in now. Color it in. And we need the distance from the centroid to the middle of that. Now that is that's 0.095, isn't it? Yeah, I think so. So we go 0.095 times your 0.01 times 0.1. That's it, guys. This should give you your first moment of area. All right. Let me do that and see what I get. Here we go. 0.07 times 0.01 times 0.04 plus 0.095 times 0.01 times 0.1. Well, I got an answer. I'm getting 1.23 times 10 to the minus fourth meters cubed. We think we know what Q is now. Look here. So what we're going to do is we're going to take the V and the Q, the I and the T, put them all together, and we're going to get our shear stress at that location. Go for it. Okay, now the V is 20 e to the third.
I'm sorry, Dr. Griffin.
Yeah, go ahead.
I'm confused on how you got the 0.07. Where did that come from?
Thank you. Thank you for asking. Now, Heath, I colored this little rectangle right here. You were with me on that?
Yeah.
And what we need is the distance from the center of the whole dang thing to the middle of that colored area. That's what this is. You got to go from the centroid times the area. Now the area you don't.
Centroid to centroid.
Yeah, it's centroid to centroid. That's another way of putting it. You don't have any trouble with the area. 0.01 times 0.04. I think you're probably all right with that. The 0.07 is what's bugging you. Well, see, from here all the way up to the top is 90. All the way to the very top is 100. But see, it's 50 to here, 40 to there. It's 90 up to here. But see, you subtract 20 and you get 70. So it's 0.07. It's 0.07 or 70 millimeters from centroid to centroid.
And then the 0.095 comes from the very bottom to the top, or to that first shaded part.
It's from the centroid of this to the centroid of that.
Okay.
See, it's 90 from here up to here, but then you got to go 5 to the middle of that 10, see? That make any sense at all?
No, that makes sense. I was just wondering because I can't see from it's very low pixel on my screen.
I believe it. You really need to just draw a scale drawing like I did on your paper where you can see it. But this is how you do it. And now we're going to find, well, we did that already. We got 21 something megapascals. Now we're going to get the shear stress. All right, I'm plugging all that stuff in now. We're going to take V, which is 20 e to the third, times Q, which is 1.23 e to the minus 4. We're going to divide by this I. I still have it down here at the bottom. 2.2926 e to the minus 5. And divide by the thickness, and the thickness is 0.01. See, the thickness is 0.01. So divide by 0.01. And boy, Jove, I get an answer that I don't like. Let me start all over again. I must have pushed the wrong button. V is 20 e to the third. Q is 1.23 e to the minus fourth. I is 2.2926 e to the minus fifth, and T, the thickness, is 0.01. Okay, here's what I'm getting. I'm getting 10.73 megapascal. Now let's look and see how we did. The nice thing about these fundamental problems is they have answers in the back. Let's go back and see F83, and we'll see what they said. F83, F83. Okay, now they said 21.8. Well, hey, Shazam, that's what the book says. They said 21.8. Now they even have it drawn as compression. See it pushing in there? And then they said the shear stress is 10.7. The book says 10.7 megapascal in the back of the book. Hey, we did good. We got what the book got. We're happy with that. Now let's do a Mohr circle to find out what the maximum stresses are, shall we? We've got the shear stress and the normal stress. We can draw a Mohr circle now, but I need the room, see? So why don't we make some room here? You got all this in your notes. We're gonna make some room. Let me write this shear stress up here where I won't lose it. It's 10.73 megapascal, and the normal stress is -21. I just need some room. Okay, so say goodbye to all this stuff. There's your important equations. Okay, now we're going to do a Mohr circle. All right, here we go. Now we have compression. The normal stress is 21.8. The minus means it's pushing, it's compression. And then the shear stress is 10.73 megapascal. Okay, now we're going to do a Mohr's circle, and you know how to do that. You draw your normal stress axis. Here goes. And your shear stress axis. And then you go 21.8. Oh, well, now wait a minute. Auga, that's compressive. So that's negative, isn't it? So you got to go 21.8. Holy cow, I don't know if I can. I can't use that scale. We'll use inches, I guess. Okay, we're going to go 21.8. Here goes. That puts you right there. I'm using inches. I went 20. This here is 21.8. And I went negative because it's compression. You can put a negative if it makes you happy. Now this is going down, so I got to go up 10.73. Well, I'm using inches, so 10.73 puts you right about there. That's 10.73 megapascal. 21.8. Now notice there's no compressive or tensile normal stress at all. So that's zero. Zero. Doesn't have any. I don't see any sigma y. Do you? Doesn't have any. It's zero. And so you're just right there. And if you went up on that's your anchor point right there. Call it point P. There you go. If you went up on that, you got to go down here. You go down 10.7. Okay. Now wait a minute. Is it 10.73? I made that too dang big. Just a minute. 10.73 would be more like about like that. I was using the wrong scale. Now I'm going to go down 10.73. And I think it puts me right about there. And now I'm going to draw the Mohr circle diameter. Ta-da! Okay, now this is 21.8. So what's half of 21.8? I can handle it with my calculator. It's 10.9. This distance here is 10.9. Of course, that's 10.9. And this distance here is 10.73. So I can get the diameter of my Mohr circle. I wonder if I did this before. Let me see if this is what I did when I did this before. We're doing a Mohr circle. If you just tuned in for this problem, they didn't ask us to do this. No, we're doing it right. Everything's looking really good. Well, no, wait a minute. I must have done it wrong here. Okay, now just a minute. No, I think we're doing it right. I think we're doing it right. Okay, we're going to draw a Mohr circle now. Here goes. Well, it's going to kind of go like this. Our artist's rendition of the Mohr's circle. There it is. That's not too terribly bad. Well, I think you could get it nicer if you measured carefully. But you know what? The most important item on here, can you see the maximum stress is right there. That's your maximum stress. And I'll tell you what it is. It's 10.5. What do we say? 10.73. Yeah. Is that the? I got lost what I was doing. We need the diameter. Here's what you're going to have to do. You're going to have to go. I had a senior moment. We need this. We need half of that, don't we? What's half of 21.8? It's 10.9. See, I can't read my own writing. That's a 10.9. Yeah. I can't read my own writing. And if I can't read my own writing, how are you expected to read it? Good question. That's 10.73 right there. Okay, now here's what we're going to do. We're going to take 10.9 and 10.73. We're going to take the square root, and that's going to give us the diameter of our Mohr circle. Okay, here goes. 10.9 squared plus 10.73 squared, square root. Did you get the diameter of your Mohr circle to be 15, rounded off to 3 megapascals? We are most interested in this maximum compressive stress right there. And I tell you what it is. It's
Mr. Griffin,
yeah.
isn't it supposed to be radius rather than diameter?
You know what? I think I owe Coy. That's Coy's voice. I think I owe Coy a thank you point. That is the radius, Coy. I'll put it up here for you. Good going, Coy. Good going. Proud of you. But I still think it's 15, and I think that's what this is. And if you want this value here, you have to add the 10.9 to it. And
You're
so,
cutting out really bad.
oh, here, let me take this microphone. Thank you for mentioning that. And see if that'll work any better. Now we're going to add these up, and
Oh, it's still really, really bad.
it's still really, really bad. Gosh, I don't know what to do. Try that. Uh-oh. How are we doing now? Doing better, maybe, I hope. Testing 1, 2, 3.
If you said anything, it's still as bad.
Oh, gee. Oh, I don't know why that happens. But you can hear me, right? It's just kind of fuzzy.
No, it's not fuzzy. It's like robotic auto tune.
It's like the guy at the drive-in Burger King. Don't they have the most horrible audio reception on those drive-in voices? I can't understand what they're saying. I want a hamburger with cheese and so forth.
It's about enough, like at least I can't even understand what you are saying. Like I can hear you're saying words, but I have no idea what they are.
Oh no.
Yeah, on my end, I don't even hear any words. It's just like a robotic auto tune.
Yeah, no, I can like hear words, but it's like sounds very robotic and it just completely is cutting out to where like, you know, you're only like certain syllables of the robotic. sound.
I'll tell my daughter about it. I don't know. Maybe if I hold the microphone. What if I hold the microphone closer? Is that bad? Or very bad, bad, bad? Hold the microphone closer. Bad, bad, bad. What do you think, Kristen? Bad, bad, bad. Hold the microphone closer. Kristen, what do you think? Pretty bad. She's not going to answer me. What if I hold it farther away? How about that, Kristen? I'm holding it farther away. Well, what do you say? Or anybody? Allison? Unmute and tell me what, can you hear me? Can you hear me? Kristen, unmute.
It's not any better. I have no idea what you're saying.
Oh, no. Oh, no. Okay, well, let me try plugging it in a different place here. There's another plug. Just a minute. Try that. What's that like?
There's like a little pop-up above you that says that your bandwidth is low.
Uh-huh.
So I'm not sure if that has something to do with why you're not coming through.
Oh, well, now you're coming through beautifully. I hear you perfectly, but me, it's still bad.
I would probably maybe suggest using a different, what do you call it, browser for the next one.
Oh, a
Maybe
different.
see if that helps
Well, I'm using that.
for like the next session.
Okay, I'm using that Chrome thing, whatever they call that.
Because now the video is not even working for me, and it says that your bandwidth is also low.
Oh no, something about a bandwidth. Oh gee. Okay, well
Okay.
I don't know what to do. Let me finish this, guys. Can you guys read the? Can you read this? This is 26.2 megapascal. Can you read that? It's the compressive normal stress. That's the most important item, and you can't understand what I'm saying. Dang. Okay. Well, let's finish up, I guess. I'm sorry. Let me give you some homework not to turn in. Okay, well, we did that, and I hope that was a good review. But let's give you some homework to not to turn in. Let me erase all this. In other words, it's a disaster. Can you guys read that? Can you read that? Pick on Eric. Eric, unmute. Eric Jones. Can you read that? Yeah, there you go, Eric. Can you read that, Eric?
Yes, I can read it.
Good. Don't turn it in. Just have it ready for us. We'll talk about it Thursday. Thursday, we'll talk about it. Okay. Well, we're going to wrap up. That was good for today. We had a review. And what do we do next? There's a lot of stuff I'd like to study. The next big topic, let me tell you that, and then we'll quit. Our next topic is going to be buckling of columns. It's an important topic, and it's let me find it here. Chapter 13. Buckling of columns. Well, I guess that's going to have to be it for today because my microphone isn't working right. But I'll work on it, guys. I'll see you, some of you at 1 o'clock, I guess, and the rest of you when I see you, okay? So adios, muchachos. I'm going to close for today.
I don't know if you can hear me, but if so, hopefully it's working when we come back in a little bit for thermo.
I hope so. I'm all for that. I'm hoping it's working. We'll see what we can do. We'll see you then. Thank you. Bye-bye, everyone.
Bye.